All right, so we're going to start talking about sequences today. A sequence is basically a list of numbers. Each term in a sequence is called a term. And you can have a sequence which consists of a certain number of terms. That's called a finite sequence. So for example, this sequence has the terms 1, 3, 5, 7, 9. It's got 5 terms. You can have 5 terms, it can have 522 terms, it can have 3,024 terms. The point is we know exactly how many terms are in there. An infinite sequence is one that has an infinite number of terms. For example, this one, 2, 4, 6, 8, ... This is a never-ending sequence. Okay, and it's got an infinite number of terms in there. So that's the difference. One ends, one does not. If you look at these two sequences, you can tell that there's a pattern. The first is all of the odd numbers starting at 1. The second is all of the even numbers starting at 2. And if it says ... then we know how to progress through this sequence, right? It's basically all of the even numbers. Sometimes it's not as clear as that. And in cases like that, you will be given an explicit formula so you can calculate very quickly the nth term of the function. Even in this term, even in this sequence, if you wanted to calculate, for example, the, 967th term, it'll be easier if you have an explicit formula that gives you an expression that you just plug in numbers to and you can get that term, right? Okay. So the first couple are pretty self-explanatory, and you've been doing things like this ever since you were very, very young. So in the first case here, let's find the next 4 terms in the following sequence. What do you see here? How do you progress from one term to the next? You subtract 4, and make sure to try it out for the next few terms as well, just to make sure that they're all the same. So you subtract 4, sure enough, you subtract 4. So if I wanted to find the next 4 terms, what would they be? Negative 13, negative 17, negative 21, negative 25. What about in part B?
Minus.
We subtract 3, then 5, 7. So you're subtracting consecutive odd numbers, right? So what would be the next step? You would subtract 9 and you get negative 6. And then you subtract 11 and you get, and you subtract 13 and you get 30, and you subtract 15 and you get negative 45. Okay? All right. In this case, you want to find the next 4 terms. Now here you are given an explicit formula. And you're given your notation A subscript n. So each term in a sequence is labeled A subscript 1, A subscript 2, and so on and so forth until A subscript n. Okay? If I want to find the first 4 here, I first have to find A subscript 1. In this case, n is equal to 1. So when I plug it into this formula, if n is equal to 1, then I have 1 cubed plus 1 equals 2. Okay? Now, the second term is A subscript 2, meaning n is what? 2. So it'll be 2 cubed plus 1, 9. A subscript 3 has n equal to 3. So it's 3 cubed plus 1, which is 28. And A subscript 4 is 4 cubed plus 1, 65. Okay, so those are the terms in the sequence. So it's 2, 9, 28, 65. Okay? Now, a recursive sequence, a recursively defined sequence, will start off with a few values, 1 or 2 values or 3 values, And the ones that follow will always be derived from the numbers that come right before it. Okay? So for example, in order to find the 7th term, you have to use the 6th term. In order to find the 8th term, you have to use the 7th term, and so on and so forth. Okay? So you use the 2nd term to find the 3rd, the 3rd term to find the 4th, the 4th term to find the 5th. Here's an example of a recursive formula. You're given that A1 is 1, and all the other ones, AN uses what? AN minus 1. Which one is AN minus 1? So if AN, if you're trying to find A4, okay, you have to use which one? AN minus 1, 4 minus 1, 3. Okay? Plus 2. So to find the 4th term, you take the 3rd term and you add 2. Okay? Let's look at this example here. We want to find the 4th term. So basically we have A1, A2, A3, A4. What is A1? We're told that A1 is 3. All right, let's find A2. To find A2, I'm going to use this formula here. And it's 3 times N minus 1. If I do N minus 1, it's 2 minus 1 minus N plus 2. So this is going to be 3 times. Now, A2 minus 1 is what? It's A1. How much is A1? 3. Minus 2 plus 2. This gives me 27. I'm sorry, 9 minus 2 plus 2 is 9. Okay? Let's find the next one, A3. So for A3, I'm going to do 3 times N minus 1, which is 3 minus 1, so it's going to be A2, minus 3 plus 2. This is 3 times what? What was A2? 9 minus 3 plus 2. So 27 minus 3 is 24, plus 2 is 26. Now let's find A4. It's 3 times N minus 1, N is 4, 4 minus 1 is A3. A3 is just code for the 3rd term. Minus N, which is now 4, plus 2. So this is 3 times, what was the 3rd term? 26 minus 4 plus 2. How much is that?
26.
76.
Yeah, in total.
In total, it's 76. Okay, so that's A4. That's the 4th term. Any questions here? Yes, no?
No, I just looked at the next one.
So we use the this term Fibonacci sequence comes up all the time in movies mostly, right? People who want to sound smart in the movies, they say, "Oh yeah, that's just a Fibonacci sequence, or that's just a Fibonacci series." So all it is it's a sequence.
Not 1 plus 2 plus 3.
Right, well, yes, it's a sequence that uses a recursive formula, okay? And to find each term, you have to add the 2 terms that come right before it, okay? So the formula is this, and please be careful in your packets. It's supposed to say A2 here, but I think it says A1. So please fix that. So now, it tells us that A1 is 0, A2 is 1, And we want to find the fourth term. So this is A1, A2. We need A3, and eventually we need to find A4. Okay? All right. To find A3, n is equal to 3. Okay? So it's supposed to be A, n minus 1 is 3 minus 1, plus A, n minus 2 is 3 minus 2. So A3 is A2 plus A1. Okay? Too many A's. What does all this garbage mean? It just means to find the third term, you add the second and the first terms. Okay? What are the second and the first terms?
1 and 0.
1 and 0. So A3 is 1. Okay? A4, we're going to add A3 plus A2. We're going to add 1 plus 1, and we're going to get 2. Okay, so for the Fibonacci sequence, to find the next term, so if we were to find the next term now, to find this one, you add the two numbers that come right before it. Okay? Huh?
That's a hard one.
That's a hard one. Yeah. So here's an example where the Fibonacci sequence comes into play in nature. If you have a tree, month number 1, you have 1 branch, right? Month number 2, you have 1 branch again. Month number 3, you get 1 more branch, so now you have a total of 2. Okay? The next month, the number of branches increase in a Fibonacci series. Okay, so the next month, you'll get another branch here. So you'll have this plus the ones you had before. You see what I mean? Yes or no?
So it's 1 plus 2.
Okay.
And then that.
So you're going to get, alright, so you're going to get 3. Now the next month, okay, now we're here. You're going to get 1 branch here and another branch there. So it's going to be the 2 branches that you had before added to each other. 3 plus 2 added to each other, 5. Okay, so here's an example where the Fibonacci series or the Fibonacci sequence comes into play in nature. Okay, and it's everywhere around us. In here, okay, and I'll get you guys some more videos eventually.
What's that note?
All right, remember when we talked about functions? We said that a function could, as x approaches infinity, a function could approach a certain value, right? And we said that that meant that it had a limit. So for example, if you have a function that goes like this, as x approaches infinity, this function approaches 0, right? Mm-hmm. So we said that it had a limit. Or if you look at it in this end, on this end, as you approach negative infinity, it goes up to infinity, so we said the limit wouldn't exist, right? Or the limit was infinity. Now, sequences can also approach a certain value, or the numbers could just keep increasing and increasing and increasing to infinity. So, for example, if you look at the sequences that we started out with here, okay, these are just going to increase forever and ever and ever. So 2, 4, 6, 8, and then we're going to go into the millions and the trillions and the infinity, right? You can, however, have sequences where, as the terms progress, the numbers will approach one specific value. If that happens, if the values will approach a specific value, then we say the series converges or it's convergent. The sequence is convergent. If the numbers just keep increasing to infinity, then we say it's divergent. And that'll give you a little bit of a context for the title of the movie, right? So the sequence will either converge or diverge. And that's what we're going to do here. We're going to figure out whether or not these will converge or diverge. What we're going to do is we're going to come up with the first few terms of the sequence, plot them here, and just get a visual of what's happening. All right. So in the first case, we want to find A1. and that's going to be